Welcome student. We are discussing CH1501 General Chemistry Unit 3A Atomic Structure and Wave Mechanics, and today we are going to discuss regarding the significance of quantum numbers and shape of orbitals and various energy levels. I am Dr. Devang Pandya, Department of Chemistry, St. Xavier's College Autonomous, Ahmedabad. Point to discuss today are significance of quantum numbers, then radial and angular wave functions, shapes of S, P and D orbitals and its characteristics, and variation of orbital energies with atomic number and energy level diagram. Students, most of these topics which we are going to discuss today, the points you are familiar with. I need to give a little insight in it so that you have a little depth idea about the different points which we are going to discuss today. Out of this, the key points we're going to discuss is to completely describe an electron in an atom. For quantum numbers are needed. Energy, to define energy we required n principal quantum number. For angular momentum we required L, azimuthal or secondary quantum number. To define the orientation and magnetic property we required magnetic moment quantum number, that is m subside L, and the spin associated with the electron, that is spin quantum number, represented as m subside S. The first quantum number describes the electron shell or energy level of an atom. The value of n ranges from 1 to the shell containing the outermost electron of that atom. The dynamics of any quantum system are described by a quantum Hamiltonian H. And as I already have said in my previous lecture, Hamiltonian is a scientist who has defined and given hundreds of mathematical equations based on an imaginary waves on an imaginary planet, and on that Hamiltonian's equations, Schrödinger have given a wave equation to define the probability of finding electrons surrounding the nucleus. Terms which we are going to use here: angular momentum, the vector product that describes the rotatory inertia of a system about an x. Quantum, the smallest possible and therefore indivisible unit of a given quantity or quantifiable phenomena. And quantum number, one of certain integers, of half integers or half integers that specify the state of quantum mechanical system, such as an electron in an atom. While the work of Bohr and de Broglie clearly established that electrons take on different discrete energy levels that are related to the atomic radius, their model was a relatively simplistic spherical view. To represent that spherical view, we represent the atom. There was an appreciation that the energy level of an electron was related to the principal quantum number n. However, there was no numerical means of classifying additional aspects of an electron's motion in space, such as its orientation or either the direction, etc. In 3 dimensions, the solution of the Schrödinger equation provided a set of 3 additional quantum numbers that could be used to describe electron behavior even in more complicated many electron atoms. This was in contrast to previous work that focused on one electron atom, such as hydrogen. The question of how many quantum numbers are needed to describe any given system was no universal answer. For each system, one must find the answer by performing a full analysis of the system, that is atomic system. Formally, the dynamics of any quantum system are described by a quantum Hamiltonian H applied to the wave equation. There is one quantum number of the system corresponding to the energy, the eigenvalue of the Hamiltonian. There is also one quantum number for each operator. Operator is nothing else, is a mathematical symbol represented by any mathematical symbol, and it can operate on a function and change the function into another, and that commutes with the Hamiltonian and satisfy the relation of the Hamiltonian on the operator is equal to operator on the Hamiltonian. Note that the operators defining the quantum numbers should be independent of each other. Often there is more than one way to choose a set of independent operators. So in different situations, different sets of quantum numbers may be used for description of the system. The most prominent system of nomenclature spawned from the molecular orbital theory of Frederick Hunt and Robert S. Mulliken, which incorporates Bohr's energy level as well as observation about electron spin. The model describes electrons using 4 quantum number, that is the energy quantum number or a principal quantum number defined or denoted as n, angular momentum quantum number denoted as small l, magnetic moment quantum number defined or denoted as m subside l, and spin quantum number as m subside s. It is also the common nomenclature in the classical description of nuclear particle states like proton or neutrons. Quantum numbers. These 4 quantum numbers are used to describe the probable location of electron in an atom instead of an exact position or any momentum value. As we have studied in uncertainty principle, it is impossible to measure the exact position and momentum simultaneously. We can indicate the probable density location of a particle, as already I have given you the example that if somebody will ask you at this point of time where is your mom, and if it is the time of cooking, you probably says that your mom would be in the kitchen. So that is the most probable area where she would be, but it may be a chance that she might be somewhere out from the kitchen, or it may be chance that she might be in the kitchen. So that way you can indicate just the probable location rather than the exactness, and much in the same way we can locate the probable location of an electron in an atom rather than the exact position. So we have the quantum numbers over here. Principal quantum number, that is n, value is neither 0 nor negative nor in half integer. It's a full whole number, 1, 2, 3, 4 and so on. Angular moment quantum number denoted as L, and it has values 0, 1, 2, 3 up to n minus 1, where n would be the principal quantum number. And magnetic quantum number m subside L have value minus L, 2 minus 1 to 0 to 1 to plus L. It means minus L to 0 to plus L. And last not least, spin quantum number m subside S, that is plus 1 by 2 minus 1 by 2. That means plus half and minus half. Now let's begin with the principal quantum number, and the principal quantum number will define the energy levels, different energy levels from the nucleus. The first energy level defined as n is equal to 1, which is represented as k shell, n is equal to 2, that is L shell, n is equal to 3, that is M shell, n is equal to 4, that is N shell, and that is the way we can represent K, L, M, N shell. and in K shell maximum 2 electron can occupy. In L subcell we have 8 electrons maximum occupied. In M subcell 18 electrons would be there, and in N there would be 32 electrons. So that is the way we can represent the Bohr atomic model, and we can fill up the electron into this, which represent the energy of electron. And that is why principal quantum number is also defined by this energy equation, minus 2 pi square mz square e raised to 4 n square h square, where n represent the principal quantum number. If I will put 1, then it will give us the energy associated with the first energy level. If I will put n is equal to 2, it will give us the energy value for the second energy level, and that way we will going to get the different energy levels in this principal quantum number. The first quantum number describes the electron shell or energy level of an atom. The value of n ranges from 1 to the shell containing the outermost electron of the atom. For example, in cesium, the outermost valence electron is in the shell with energy level 6. So an electron in cesium can have n value from 1 to 6. For particle in a time-dependent potential per Schrödinger equation, it also labels the nth eigenvalue of Hamiltonian. The energy E with the contribution due to the angular momentum, the term involving J2 will be left out. This number therefore has a dependence on the distance between the electron and the nucleus, or we can say the radial coordinates r. So principal quantum number can be obtained from the radial coordinates r. The average distance increases with n, thus quantum state with different principal quantum numbers are said to belong to different cells, different energy levels. Now the second one is the azimuthal quantum number, that is secondary quantum number, where you can see L is equal to 0, we have s orbital, L is equal to 1, we have p orbital, L is equal to 2, we have d orbital, so on. So it will going to give us information regarding the different energy level. The second quantum number, known as the angular or orbital quantum number, describes this subcell and gives the magnitude of the orbital angular moment through the relation. In chemistry and in spectroscopy, when we have L is equal to 0, it is called an s orbital, L is equal to 1, a p orbital, L is equal to 2, a d orbital, and L is equal to 3, an f orbital, where s stands for sharp, p stands for principal, d stands for diffuse, and f stands for fundamental. The value of L ranges from 0 to n minus 1, because the first p orbital, that is L is equal to 1, appears in the second electron shell, that is n is equal to 2. The first d orbital, that is L is equal to 2, appears in the third subshell, that is n is equal to 3, and so on. So that is why the value of L ranges from 0 to n minus 1. In chemistry, this quantum number is very important since it specifies the shape of an atomic orbital and strongly influences chemical bonds, bond angle, and different kind of information related to angular moment of the electron. The third one would be the magnetic quantum number. When Professor Linde is working in his lab, he saw that there should be a very thick shadow of a spectrum line, and at that time there shouldn't be any magnetic field applied to the atom, and he got the spectrum line which is very thick. So he thought, let me put the atom into a high magnetic field and take the spectrum again. When he do that, instead of a thick sharp line, he got thin sharp lines, 3 different thin sharp lines for the atom which contain p orbital, and on the base of that he stated that when the atom is placed into a magnetic field, the spectrum line will going to get 3 different energy levels, and that is how he defined px, py, and pz for the p orbital. So the orientation and the degeneracy introduced by Professor Linde, stating the magnetic quantum number. The magnetic quantum number describes the energy levels available within a subcell and yields the projection of the orbital angular moment along a specified axis. The values of m subside L ranges from minus L to plus L, minus L to 0 to plus L, with integer steps between them. This S subcell where L is equal to 0 contains one orbital, and therefore the value of m subside L, that is magnetic quantum number for an electron in an S subcell, will always be 0. The P subcell where L is equal to 1 contains 3 orbital in some system depicted as 3 dumbbell shaped clouds. So m subside L of the electron in P subcell will be minus 1 to 0 to plus 1. The D subcell where L is equal to 2 contains 5 orbitals with m subside L values of minus 2, minus 1, 0, plus 1 and plus 2. Similarly, for F subcell L is equal to 3 contains 7 orbitals with m subside L values of minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. The value of the m subside L quantum number is associated with the orbital orientation. The spin projection quantum number or spin quantum number defined by Gaudsmit and Uhlenbeck. What they have done? They have taken a strong magnetic field, and through the strong magnetic field they passed a stream of hydrogen atom, because hydrogen contains single electron. So they want to know whether the electron present in a different hydrogen atom have similar spin or a different spin. So when they passed the hydrogen stream from a magnetic field, they found two side deviation of certain hydrogen atom towards northern side, certain hydrogen atoms towards southern side, and on the base of that they defined that within a similar kind of atom there should be a different spin orientation containing electron present, and on the base of that they have given a quantum number known as spin projection quantum number. The fourth quantum number describes the spin, that is intrinsic angular momentum of the electron within that orbital, and gives the projection of the spin angular momentum, that is S, along the specified axis. Analogously, the values of m subside S range from minus S to S, where S is the spin quantum number, an intrinsic property of a particle. An electron has a spin S is equal to 1 by 2, that is half. Consequently, m subside S will be plus or minus corresponding with the spin and opposite spin. Each electron in any individual orbital must have different spin because of the Pauli exclusion principle. Therefore, an orbital never contains more than 2 electrons in one subcell. For example, the quantum numbers of electrons from a magnesium atom are listed below. Remember that each list of the number corresponds to n, that is principal quantum number, L, that is azimuthal quantum number, m subside L, that is magnetic quantum number, and m subside S, that is spin quantum number. Two s electrons represent n is equal to 1, L is equal to 0, ml is equal to 0. As already I would like to represent in this way: n is equal to 1, L is equal to 0, m subside L value 0, m subside S value plus half. Or either you may represent as the principal quantum number, n is equal to 1, L is equal to 0, m subside L value 0, and the spin may be minus half. So these two represents would be there for 2s electron in magnesium atom. the 2s electron may represented as this one, that is the electron which is there in the 1s orbital. Now this is the electron which is there in the 2s orbital, where n is equal to 2, L should be 0, m subside L value 0, m subside s value plus half. Similarly here n is equal to 2, L probably 0, and if L is equal to 0 it is s orbital, and for L is equal to 0 m subside L value also 0, and m subside s value would be minus half. So for 2 electron which is there in 2s orbital in magnesium can be represented like this one. 6 p electrons can be represented like this one, that is p orbital. So n is equal to 2, L is equal to 1, ml would be minus 1, 0, plus 1, 0, minus 1. That way you need to represent. So 1, 2, 3, 4, 5 and 6 possible arrangement would be there, and 6 electron can occupy into p orbital. This one is quite similar, you can see. So plus 1 half and minus half, and then after instead of minus 1 now we have 2 0, plus half, minus half, and then plus 1. So for m subside L value we have minus 1, 0 and plus 1, and for m subside S value for we have plus half minus half, plus half minus half, plus half minus half, and that way 6 possible arrangement is there for the magnesium. 2s electrons can be represented in 3s2. So for that, principal quantum number n is equal to 3, L is equal to 0 because it is s orbital, m subside L value would be 0 as well, and for m subside s value we have two different value, plus half and minus half. So that way we can represent the number of electron in a different subcell in magnesium element. Now this is the way we can represent a tabular form for different orbital. This is S, S1s, 2s, 3s, 4s, 5s, and you can see there should be this is the diagonal part of the s orbital, and you can see different nodal parts inside the structure as well. So this table relating to the quantum numbers to orbital shape, the relationship between the three of the 4 quantum numbers to the orbital shape of simple electronic configuration atom up through radium up to 2088. The 4th quantum number, the spin, is a property of individual electrons with a particular orbital, and each orbital may hold up to 2 electrons with opposite spin of the direction. Now here also you can see cell is n have different L values 0, 1, 2, 3 and so on up to n minus 1, and we have subcell. That subcell will be s orbital, p orbital, d and f, and as far as s is concerned, m subside L value would be 0. For L is equal to 1 we have m subside L value would be plus 1, 0, minus 1, so it represents p orbital, and for L is equal to 2 we have m subside L value would be plus 2, plus 1, 0, minus 1, minus 2, so that represents d orbital, and for L is equal to 3 we have m subside L value that represent f orbital, plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. So that is the way we can represent a different quantum number, and that different quantum number give us idea about different cell, subcell, their energy level, their shape, their behavior, and on the base of that we can define the property and stability of atom. And if we know the stability and property of atom, we can represent bond angle and molecular formation. If we know the molecular formation, we can represent different property associated with the molecule, and that is the way different research can be taken place in chemistry. Now radial and angular wave function, and this radial and probability distribution of radial angular will represent different energy level, node area, etc., and that we can find out over here. This hump will represent the maximum probability of finding electron, and this line which touches to the distance from the nucleus that represent the nodal part where there shouldn't be any electron, like this nodes is indicated over here. Or in the whitish part there is less probability of finding electron, in this orange part there is maximum probability of finding electron. Much in the same way it can be graphically represented like this one as well. So how this representation can be made, let's learn. Radial distribution function that is represented by 4 pi r square psi square. It is often useful to know the likelihood of finding the electron in an orbital at any given distance away from the nucleus. This enables us to say at what distance from the nucleus the electron is most likely to be found, and also how tightly or loosely the electron is bound in a particular atom. This is expressed by the radial distribution function. For s orbital, the radial distribution function is given by multiplying the electron density by 4 pi r square. And that radial distribution you can see over here, where you can see the behavior of electron and how the wave function get changed into different case A, B, C, D, E, F, G, H. You can see how different movement we're going to observe regarding the electron within the atomic structure, and that will going to give us idea about different cell, subcell, etc. And that also indicates the difference or distance between the nucleus and the electron. In short, we can find out the radius of an atom as well. Wave equation. An orbital is a mathematical function which called a wave function that describe an electron and its behavior in an atom. The wave function of the atomic orbitals can be expressed as the product of a radial wave function r and angular wave function gamma or y. Radial wave function for a given atom depend on only upon the distance from the nucleus r, and that can be represented as r pi 4 pi square r. Angular wave function depends only upon the direction and in effect describes the shape of an orbital. Psi is equal to radial function into angular function, that is r into y, and in certain different references instead of y, angular wave function can be denoted as a as well. So r into a you may write, r into y you may write. The first orbital, that is n is equal to 1, l is equal to 0, m subside l is equal to 0, and it is a k shell, and where we can have s orbital. In this plot we can see the effect of the factor r in first 1s orbital, that is r represented as r1s into small r, that small r represents the radius. Here r1sr goes to a0, that is Bohr radius at r is equal to 0, while u1sr goes to 0. The factor of r in u1sr also introduce a peak at 1AO. There is no node for 1s state. The probability density goes to 0 at r is equal to 0. It means that the probability of finding the electron at nucleus is 0, and that shows also a peak at AO, which is the same as Bohr radius, and the peak value is 0.54 angstrom, and that represent the radius of atom which contain one electron in 1s orbital, means this may be the radius of hydrogen atom. Conceptually, peaks in the P and L are radii near which an electron in a state n L m subside L is most likely to be found. Because of the gradual decay of this value P and L, R on the large R side of this peak, the calculated mean radial position turns out to be larger than the location of the peak. Following figure will going to give us the idea about the 1s orbital. You can see this is the 1s orbital where there should be this value, where near the nucleus you can see probability of finding electron would be 0, and we need to find out this maxima, and that maxima when you are going to measure over here, it will going to give us 0.54 angstrom, which is the radius of atom. So that is the maximum probability we can found over here for the electron, and that is represented as 0.54 angstrom, which is the radius of 1s orbital, or we can say the radius of a hydrogen atom. The second orbital, that is n is equal to 2, L shell, L is equal to 0, M subside L 0, L is equal to 1, M subside L is equal to 0 or plus or minus 1. So two kind of situation is possible over here. For L is equal to 0 or 1, we will going to discuss the 0 first. The 2s orbital function in the figure, which I am going to show you later on, decays R to infinity more gradually than 1s U1s over. Moreover, the 2s radial probability density has two peaks at 0.76 AO and the next one as 5.42 AO. The height of the peak nearest to the nucleus, that is 0.052, is much smaller than that of the outer peak, that is 0.19. The presence of small peak in this relatively near the origin is called the penetration. So here you can see the penetration, and this one is the node area, and then after this is the another peak where we found the presence of another electron, and that is a distance 0.76. so this is going to be the radius of 2s orbital, that is of helium. So that way we can find out the distance from the nucleus and the behavior of electron. Now 2p function in this figure 9.7 differs strikingly near the origin from the 1s and 2s functions, and because of L is equal to 1, the barrier terms in the R radial equation from 0 has a classically forbidden region near the origin. So here forbidden region, and this is a maximum peak, so you can see that it is quite near to the 1s. So there is very minor energy difference between a 2p and 1s, and 2p have only one peak while 2s have two peak. So that way we can find out. So here for px, py and pz we are going to get this different values. Now shape of orbitals. An orbital is the region of a space around the nucleus within which the probability of finding an electron of given energy is maximum. Therefore, the shape of the orbital is actually the electron cloud which appears in that particular shape. Based on this theory, various type of orbitals with various shapes are being designated as S, P, D, F shape of S orbital. The probability of finding the electron belonging to S orbital of any main cell is identical in all directions at a given distance from the nucleus. It means it is symmetrically spread in all the direction equally. Therefore, S orbital is actually spherical and symmetrical around the nucleus. Depending upon the number of electrons, there can be more than one s orbital in the atom. Although s orbitals are all symmetrical, there are regions where the probability of each electron is going to be 0. The intermediate regions between two s orbitals where the probability of finding electron is 0 is called as node area. In general, that is an s orbital has n-1 node. Secondly, the size and the energy of s orbital increases as the number of orbital increases. You can see here the different a camera has been taken with electron microscope high resolution, and numberless clicks has been taken, and then we found that each time the position of particle get changed, and when we impose those photographs on each other, we're going to found this kind of dotted cloud near the nucleus, which is round in shape, so it represents s orbital, which is spherical in shape. Now shape of p orbital. Probability of finding p electron is maximum in two lobes present on the both side of the nucleus. This leads to a dumbbell shaped orbital for the p electrons. Similar to the node of s orbital, a node plane passing through the nucleus exists in p orbital as well. P orbital have an additional characteristic nature of directionality, due to which three different orbitals, namely py, px and pz arises. These three p orbitals have equal energy and are known as degenerate orbitals. Here you can see that px, pz, px and py. Three orientation L is equal to 1 as required for a p orbital. M subside L value would be +1, -1, +1, -1, +1, 0 and +1. Now shape of d orbital. The number of the family of hydrogen atom wave functions with two angular wave functions and so two nodal planes through the nucleus are called the d orbitals. There are 5 different kind of d orbitals differing by the orientation of the clover leaf shape. The 5 different kinds of d orbitals are called dz square, dyz, dxz, dzx, dxz square, dyz, dzx and dxy and dx square minus y square. The lowest energy members, the 5d, each have one radial loop moving out from the nucleus. The second lowest energy members for d, which have two radial loops, etc. It is to be noted that in an atom, each electron in each cell is identified by what is known as quantum numbers. These are the orientation of d orbital: dx square minus y square, dz square, dxy, dyz and dzx. And this is the nodal plane which I am talking about, which is passing through it, where it represents zero density of electron in the node area. This is the shape of combined s, p and d orbital: s orbital, p orbital, d orbital, and you can see mixed dumbbell shape, that is f orbital as well. Now variation of energies with atomic number and energy level diagram. Student, you know that when electron is filled in the energy level, it will fill in this way. First it enter into 1s, then 2s, then it enter into 2p. 2p is triply degenerate, so electron try to remain unpaired, and then if more number of electrons are there, it get paired up and then enter into 3s, then 3p, then 3d and 4s. There should be a interchange into 4s and 3d due to shielding effect that you know in transition metal series. So when you discuss regarding the variation of energy orbitals with atomic number and energy level diagram, 3 basic rules we need to follow. One is Aubert principle, second one is Pauli's exclusion principle, and third one is Hund's multiplicity rule. Aubert principle is arrangement of for the electron. Electrons are like old couple. When you told old people to choose from a tall storage building, they initially choose the ground floor, and if the ground floor is filled, they prefer first floor, and that way they prefer one by one the above flow. So the electron is like this one, they will prefer lowest energy level first, when if it is completely filled it goes into higher energy level. And if the energy levels are degenerate, or we can say same energy, equal energy, so they try to remain unpaired, and if more electrons would be there, then the pairing will take place. So three basic rules would be there. First one is Aufbau principle. Aufbau is a German word and its meaning is arrangement. It is not a name of scientist, please clarify this. Aufbau principle is also given by Linus Pauling. Then after Pauli's exclusion principle, what is stated that in one subcell maximum 2 electron can occupy with anti-parallel spin, and therefore quantum numbers would never be equal. And the third one is Hund's maximum multiplicity rule, in which electron when try to enter into degenerate orbital, it try to remain unpaired, and if more electrons are there, then pairing take place. So that way electron would be refilled into this various energy orbitals, and as the atomic number increase, the energy order get changed, and according to that electron will be refilled into this different energy level, and we can get the electronic configuration of an element. So with this we have completed the entire package of atomic structure. Thank you for paying attention to this video lecture, and I always try to inspire you, ask the question, because asking question is a beautiful way to gain knowledge. So this much is enough from my end. Thank you very much, friends.
Atomic orbitals. The orbital wave function or psi of an electron in an atom has no physical meaning. It is simply a mathematical function of the coordinates of the electron. However, for different orbitals, the plots of corresponding wave function as a function of r, which is the radius or the distance from the nucleus, are different. According to the German physicist Max Born, the square of the wave function, which is the psi square at a point, gives the probability density of the electron at that point. The variation of psi square as a function of r for 1s and 2s orbitals is shown here. Notice that the curves for 1s and 2s orbitals are different. It may be noted that for 1s orbital, the probability density is maximum at the nucleus, and it decreases sharply as we move away from it. On the other hand, for 2s orbital, the probability density first decreases sharply to 0 and again starts increasing. After reaching a small maxima, it decreases again and approaches 0 as the value of r increases further. The region where this probability density function reduces to 0 is called nodal surfaces, or simply nodes. In general, it has been found that ns orbital has n-1 nodes. That is, the number of nodes increases with increase of principal quantum number n. In other words, the number of nodes for 2s orbital is 1, 2 for 3s orbital, and so on. These probability density variations can be visualized in terms of charge cloud diagrams. In these diagrams, the density of the dots in a region represents electron probability density in that region. Boundary surface diagrams of constant probability density for different orbitals gives a fairly good representation of the shapes of the orbitals. In this representation, a boundary surface or contour surface is drawn in space for an orbital on which the value of the probability density psi square is constant. In principle, many such boundary surfaces may be possible. However, for a given orbital, only that boundary surface diagram of constant probability density is taken to be good representation of the shape of the orbital, which encloses a region or volume in which the probability of finding the electron is very high, say around 90%. One may ask, why do we not draw a boundary surface diagram which bounds a region in which the probability of finding the electron is, say, 100%? The answer to this question is that the probability density psi square has always some value howsoever small it may be, at any finite distance from the nucleus. It is therefore not possible to draw a boundary surface diagram of a rigid size in which the probability of finding the electron is 100%. Boundary surface diagram for a s orbital is actually a sphere centered on the nucleus. In 2 dimensions, this sphere looks like a circle. It encloses a region in which the probability of finding the electron is about 90%. Thus, we see that 1s and 2s orbitals are spherical in shape. In reality, all the s orbitals are spherically symmetric. That is, the probability of finding the electron at a given distance is equal in all the directions. It is also observed that the size of the s orbital increases with increase in n. That is, the size of the 4s orbital is greater than that of 3s orbital, which is greater than that of 2s orbital, which is greater than that of 1s orbital. And the electron is located further away from the nucleus as the principal quantum number increases. In our next video, Shapes of Atomic Orbitals Part 2, we will learn in detail about the boundary surface diagrams of p and d orbitals. Thank you.